All right, hello. Welcome to my channel. This is an educational channel where we study cosmologies and theories of everything, primarily. Things that I think are very important that you don't know anything about because they're not covered in school, um, not covered in the, public, mainstream educational outlets, but they were put together by people who spent their whole life dedicated and working on something, and they came up with something, and um, nobody's ever looked at it before, or very few people have looked at it. And so today is the 156th video that we've done on the reciprocal system of theory. This is a system of theory, or a theory of everything, that was devised by Dewey B. Larson back in the 20th century. He died back in 1990. Started his work way back in 1930 or so. And we're looking at his 1979 book right now that's called Nothing But Motion. The basic idea behind Mr. Larson's reciprocal system of theory is that we live in a universe of motion. The universe is not made out of matter, it's not made out of energy. Fundamentally, it's made out of motion. Energy and matter are actually just both kinds of motion. Motion is the relationship between space and time. That leaves a generalized reciprocal relationship between space and time. So motion is basically a fraction with either time or space as the numerator and the other as the denominator. But they come in coordinate space and coordinate time, meaning 3 or more dimensions of both space and time, and they both have their clock aspects, meaning that they both progress. Time is always getting later and later. Space is always getting farther and farther apart. We understand the time part of that. The space part of that was observed by the Hubble telescope in that all of the distant galaxies are moving away from each other. And that is the progression of space, or the flow of space. So time and space both flow or progress, and they both have coordinate aspects, meaning that they both are 3 or more dimensions. They also both come in discrete units. There is no half a unit or 3/10 of a unit of space. You either have 1 unit, 2 units, 3 units, 4 units, but only integers. And so those units are very, very small, however, so they appear to be continuous, but they are not. And 1 unit of space in 1 unit of time is the speed of light. So the speed of light is basically 1, and 1 is basically what Larson calls the natural reference system. Most systems that we understand have 0 as the natural reference system. 0 is the place that you make your measurements from, the origin. But in the reciprocal system, we measure from 1, from the speed of light. So if something's moving slower than the speed of light, it is what Larson calls a material, in the material sector. And if it's moving faster than the speed of light, it's in the cosmic sector. He uses different terms here in this Nothing But Motion book. But the idea is the same, that the universe really has those 2 different sectors, the material sector and the cosmic sector. The material sector is the one that we're used to, we're accustomed to. This is the one that where Einstein says that the speed of light is the maximum speed of the universe. Well, this is true in the material sector. In the Cosmic sector, however, the speed of light is actually the minimum speed of the universe. And so these different sectors are identical to one another, except that they are inverses of one another or reciprocals of one another. That's the reciprocal system of theory. Okay, so that's just a short overview of the system. You really need to kind of study it and understand it. If you do really get it, then you can use it yourself to derive true relations and understanding in any field that you choose. You just have to kind of figure out how to plug in the reciprocal system. Larson himself plugged it into physics and astrophysics, chemistry, astronomy, economics, metaphysics, including religion, psychology, philosophy, dream interpretation, and many other things. So Larson obviously understood the system quite well. But if you really plug away at it, take it like your high school chemistry class, you would be able to understand the reciprocal system also. And so it's not easy, but it's not. It makes things a lot simpler than, say, quantum mechanics and relativity theory. It's much simpler than that, but it's not easy. Okay, we were in chapter 6 of this book that is called The Reciprocal Relation. And this is a crucial chapter. And we were just talking about how to really understand three-dimensional time and how it's measured and the different reference systems involved. So I'm going to go back about half a paragraph and start that up, and then we'll move forward from there. Their motion in three-dimensional time is therefore linearly outward at unit speed. Unit speed is the speed of light. And the time location that we observe, the time registered on a clock, is not the location in any temporal reference system, but simply the stage of the progression. Since the progression of the natural reference system proceeds at unit speed, always and everywhere, clock time, if properly measured, is the same everywhere. As we will see later in the development, the current hypotheses which require repudiation of the existence of absolute time and the concept of simultaneity of distant events are erroneous products of reasoning from premises in which clock time is incorrectly identified as time in general. The best way to get a clear picture of the relation of clock time to time in general is to consider the analogous situation in space. Let us assume that a photon A is emitted from some material object X in the direction Y. Just in case you don't know, a photon is basically a light particle, an entity of the smallest entity of light. This photon then travels at unit speed in a straight line xy, which can be represented in the conventional fixed spatial reference system. The line of progression of time has the same relation to time in general, three-dimensional time, as the line xy has to space in general, three-dimensional space. It is a one-dimensional line of travel in a three-dimensional continuum, not something separate and distinct from that continuum, but a specific part of it. Now let us further assume that we have a device whereby we can measure the rate of increase of the spatial distance xa, and let us call this device a space clock. Inasmuch as all photons travel at the same speed, this one space clock will suffice for the measurement of the distance traversed in any motion by any photon, irrespective of its location or direction of movement. as long as we are interested only in the scalar magnitude. But this measurement is valid only for objects such as photons, which travel at unit speed. If we introduce an object which travels at some speed other than unity, the measurement that we get from the space clock will not correctly represent the space traversed by that object. Nor will the space clock registration be valid for the relative separation of moving objects, even if they are traveling at unit speed. In order to arrive at the true amount of space entering into such motions, we must either measure that space individually, or we must apply an appropriate correction to the measurement by the space clock. Because objects at rest in the stationary reference system or moving at low velocities with respect to it are moving at unit speed relative to any stationary temporal reference system, a clock which measures the time progression in any one process provides an accurate measurement of the time elapsed in any low-speed physical process. Just as the space clock in our analogy measured the space traversed by any photon. Here again, however, if an object moves at a speed or a relative speed differing from unity, so that its movement in time is not the same as that of the progression of the natural reference system, then the clock time does not correctly represent the actual time involved in the motion under consideration. As in the analogy, the true quantity, the net total time, must be obtained either by a separate measurement, which is usually impractical, or by determining the magnitude of the adjustment that must be applied to the clock time to convert it to total time. In application to motion in space, the total time, like the clock registration, is a scalar quantity. Some readers of the previous edition have found it difficult to accept the idea that time can be three-dimensional because this makes time a vector quantity and presumably leads to situations in which we are called upon to divide one vector quantity by another. But such situations are non-existent. If we are dealing with spatial relations, time is scalar because it has no spatial direction. If we are dealing with temporal relations, space is scalar because it has no temporal direction. Let me read those two sentences again. If we are dealing with spatial relations, time is scalar because it has no spatial direction. If we are dealing with temporal relations, space is scalar because it has no temporal direction. Either space or time can be vectorial in appropriate circumstances. However, as explained earlier in this chapter, the deviation from the normal scalar progression at unit speed may take place either in space or in time, but not in both coincidentally. Consequently, there is no physical situation in which both space and time are vectorial. Similarly, scalar rotation and its gravitational or translational effect take place either in space or in time, but not in both. If the speed of the rotation is less than unity, time continues progressing at the normal unit rate. But because of the directional changes during rotation, space progresses only 1 unit, while time is progressing n units. Thus, the change in position relative to the natural unit datum, both in the rotation and its gravitational effect, takes place in space. Conversely, if the speed of the rotation is greater than unity, the rotation and its gravitational effect take place in time. An important result of the fact that rotation is greater than unit speeds produces an inward motion, gravitation, in time. is that a rotational motion or combination of motions with a net speed greater than unity cannot exist in a spatial reference system for more than one dimensionally variable unit of time. As pointed out in Chapter 3, the spatial systems of reference to which the human race is limited because it is subject to gravitation in space are not capable of representing deviations from the normal rate of time progression. In certain special situations to be considered later, in which the normal direction of vectorial motion is reversed, the change of position in time manifests itself as a distortion of the spatial position. Otherwise, an object moving normally with a speed greater than unity is coincident with the reference system for only one unit of time. During the next unit, while the spatial reference system is moving outward in time at the unit rate of the normal progression, gravitation is carrying the rotating unit inward in time. It therefore moves away from the reference system and disappears. This point will be very significant in our consideration of the high-speed rotational systems in Chapter 15. Recognition of the fact that each effective unit of rotational motion, or mass, occupies a location in time as well as a location in space now enables us to determine the effect of mass concentration on the gravitational motion. Because of the continuation of the progression of time while gravitation is moving the atoms of matter inward in space, the aggregates of matter that are eventually formed in space consist of a large number of mass units that are contiguous in space but widely dispersed in time. One of the results of this situation is that the magnitude of the gravitational motion or force is a function not only of the distance between objects, but also of the effective number of units of rotational motion, measured as mass, that each object possesses. This motion is distributed over all space-time directions, rather than merely over all space directions. And since an aggregate of n mass units occupies n time locations, the total number of space-time locations is also n, even though all mass units of each object are nearly coincident spatially. The total gravitational motion of any mass unit toward that aggregate is thus n times that toward a single mass unit at the same distance. It then follows that the gravitational motion or force is proportional to the product of the apparently interacting masses. It can now be seen that the comments in the last chapter with respect to the apparent change of direction of the gravitational motions or forces when the apparently interacting masses change their relative positions are applicable to multi-unit aggregates as well as to individual mass units considered in the original discussion. The gravitational motion always takes place toward all space-time locations, whether or not those locations are occupied by objects that enable us to detect the motion. A point that should be noted in this connection is that two objects are in effective contact if they occupy adjoining locations either in space or in time, regardless of the extent of their separation in the other aspect of motion. This statement may seem to conflict with the empirical observation that contact can be made only if two objects are in the same place at the same clock time. However, the inability to make contact when the objects reach a common spatial location in a fixed reference system at different clock times is not due to the lack of coincidence in time, but to the progression of space that takes place in connection with the progression of time, which is registered by the clock. Because of this space progression, the location that has the same spatial coordinates in the stationary reference system is not the same spatial location that it was at an earlier time. Scientific history shows that physical problems of long standing are usually the result of errors in the prevailing basic concepts, and that significant conceptual modifications are a prerequisite for their solution. We will find, as we proceed with the theoretical development, that the reciprocal relation between space and time, which necessarily exists in a universe of motion, is just the kind of a conceptual alteration that is needed to clear up the existing physical situation. One which makes drastic changes where such changes are required, but leaves the empirically determined relations of our everyday experience essentially untouched. Alrighty, that is the end of chapter 6 on the reciprocal relation. What I just said was a big mouthful. I recognize that. And even as I was reading it, I was unable to follow along with what he was talking about. My recommendation for me and for you, it was to listen to this video several different times maybe at low speed. And the problem with Larson is that sometimes he just floods you with semi-familiar terms. So we learned the term scalar motion, but we might not have it like handy in our lexicon. Scalar motion is a motion that has a magnitude but has no direction. So just listen to it very slowly and make sure you understand each one of the terms before you move on to the next sentence. That's all I can suggest, and I'm sorry that it's not any easier than that. Hopefully some of you will persevere, because it is worth it if you eventually begin to understand these concepts. Okay, well, have a great day. Thanks for tuning in, and hope to see you tomorrow.